last day. We're going to finish up back where we started about learning how to read graphs. Okay, so we started with this chapter with geometry, rectangles, trapezoids, and we're going to end the chapter back with some geometry, again, reading a graph. Okay, looking at the green box, we're defining that antiderivative. This antiderivative is starting with f prime. And so because it starts with f prime, it takes it to regular f. And then we plug in our b as our upper bound and our a as our lower bound. So for our last day, suppose that your f of a actually turns out to be a constant. Okay, suppose that your f of a turns out to be a constant. So that's going to make this problem look like this. It's going to say a to b of f prime of t parentheses dt is f of b minus a constant. And suppose that it should say f of b, not just b right there. It should say f of b is unknown. Okay, so here is the unknown. And usually in math, when something is unknown, we want to get it by itself. So what would you do to both sides to get that unknown alone, to solve for it? Okay, you're going to add the c. And so that's going to end up with, and I'm going to put it in front, it'll end up with c plus the integral. All right, the point of that is that pieces can be moved around. So sometimes the variable is going to show up in a different place. The variable might show up on the right side instead of the left side. And if that's the case, that's fine, because it's legal in math to move things around from side to side and get the part alone that you end up needing to get alone. I just want you to know you have the freedom and the legality to be able to do that, to move this around. But this would end up to be a constant here. Now this is similar to the quiz where you had to start with the number 6,000 and then do something after that. Okay, on the quiz, we started with the number 6,000 and then we added the result of the first integral and we subtracted the result of the second integral. That's going to be a very common thing in word problems for you to be given a number to start with and then add or subtract from it based on that number. So it's the c, instead of plus c, it's c plus. C plus something else, and what I'm going to do with that after that. So this is what I need you to think of it as, okay? C plus something else. The C at the beginning represents where you're starting from. Now, you don't always start from 0. Sometimes you start from 6,000. Sometimes you start back far back, but that is going to be where you start from, and then you accumulate from that point forward. Okay, so if you're given a head start, I'm going to let you start here, and then you're going to accumulate from that point forward. That's why we call these accumulator functions. And so this is going to be your constant value, and then the a is your starting point, starting from that particular point, starting from point A. So I'm starting with my constant value, I'm starting with 6,000. And I'm starting at this particular day or time or something like that. And we always move forward. All right, so here we're going to do some just plain math ones, and then we'll do some like word problem ones for constant. All right, if the derivative we're given is an exponential derivative, and that is the starting point. We call that the initial value. So there are two parts to that initial value. I'm starting at the number 7 with the value of 3. Okay? I'm starting at the number 7, and I'm starting with a value already of 3. And then the question is, what would your f of x look like? That says find f of x. Okay, well, according to this model, f of x means I am starting with the value of 3, and my integral will pick up starting at the number 7, and then we'll go as far then as I need it to go. think of this from a geometric standpoint. It means you're told you're starting with an amount of 3 area, and then starting at the number 7, you're going to accumulate area after that, always moving to the right on a graph. So 3 is the quantity you start with, 7 is the position you start at, and you always move to the right. Whoops, I know what the F is. That should say e to the negative x squared.
3 is a quantity.
Say that again. 3 is a quantity. It's a value.
Like an
Okay.
area under.
It represents how much area has already been accumulated, or not necessarily area, how many gallons you already have, or how many bananas you've already done, or how much, whatever. Okay. Yeah. It would be like, I'm going to give you this much seed money, and from this point forward, you're in charge of that, and it's going to go forward. And are you going to accumulate, and is that going to go up, or is that going to go down? Kind of like the parable of talents in the Bible, where, okay, I'm going to give you 7 talents, and I'm going to give you, this many, and from that point forward, what are you going to do with that? Okay? Okay. All right, so just looking how this is going to go. Okay, our function is going to be accumulating under the square root of the sine of x. We don't know what that looks, we know what a sine looks like, and we know what a square root's going to do that to that. That square root is going to make that sine graph shrink down. It's going to get littler and littler, and it's wiggling. So we're going to start under that. Yep.
I'm just wondering, on the slide above, why is it dt and not dx?
Good question. Oh, shoot, every time I go back to an old slide, I can't erase something I already did. These both should be t's. The t it's with respect to time, okay? Because I'm moving along the time axis right now. And it's the fact that x is the upper bound is really arbitrary. It doesn't need to be x. I could have picked b, or I could have picked, it's like from 7 to, it could have been b. It's an arbitrary, I picked an arbitrary letter. It's just the t is going to tell you what axis you're moving along. And then the top value would be where you would eventually stop. Right now it's open-ended. It's like from 7 to infinity right now. I haven't set what that is, but it could be b or any other value. It just shouldn't be t. It shouldn't be the same thing. It shouldn't be the same letter, but it could be some other letter. Yeah.
So is the question when it's find if f prime equals e to the negative x squared, is that written wrong? Should that be a t, or do you have to change that x in the x squared to a t? Right.
Change it to whatever axis they're asking, whatever the units are.
So you do have to change it.
Mm-hmm.
Okay.
Mm-hmm. Okay, so let's try setting this one up. Same idea. Okay, imagine that the shape of the function is the square root of sine, and we're going to be working along the t-axis again here. So I'm going to start with what number? How much what's my seed money? 7. Okay. And then picking up at the graph, what time value will I be starting at? -1. Okay. Going to an arbitrary value of time, and then I'll be using the sign along that time axis, dt. So setting it up that way. So back to Chloe's question. The letter x is arbitrary. I could have made both of those b's. G of b is going to be that. That doesn't matter, but they told me to find g of x, so that's why I did g of x. But they could have used any other arbitrary. That's an arbitrary variable. Okay, so let's actually finish a question. Find a function whose derivative will be accumulating under the tangent curve, and we all know what a tangent curve looks like, that satisfies the initial value of f of 3 is 57, and then find f of 7. So first find f of x. So let's find f of x. F of x means starting with 57, that's what I'm given to start with. I'll be accumulating from at the time value or the position of 3. I'm going to some unknown spot, and I'll be doing that under the tan curve t dt. That's the setup of that. That's the beginning. And now to find f of 7, it means you're going to stop at 7. So I'll be starting at 3. If I was drawing this, I'd be drawing a tangent curve that picks up starting, I've already got 57 in the bank, and then I want to start at 3 and move forward to 7 and basically accumulate all the area under there. So f of 7 then would start with the 57. It would go from 3 to 7 as my stopping point of the tangent of t dt. Now, do we know the antiderivative of the tangent? That's the derivative of the tangent. Do we know the antiderivative of the tangent? No, that's the derivative again. No, you don't know yet. No. It happens to be the natural log of the cosecant, but you don't know that yet. Excuse me, cosine, natural log of the cosine. You don't know that yet. Okay? So, and do we know the geometry under the tangent curve? No. So what would we need?
Calculator.
Okay, so then we would evaluate that with our calculator. Right. Chapter 6. You'll learn that in chapter 6.
Oh, thank goodness.
All right. What method do you think we'll be learning here? Geometry. Okay. Yeah, it's good because it's nice triangles and stuff. Okay. The figure consists of 2 line segments, so we know that they're straight. We know this could be nice geometry for us. The function g is defined starting where?
At 0.
Starting at 0. Is there any initial condition value I've been given?
Yes. 3-ish. Just a little below 3.
Where do you get 3?
At x is 0.
That's the value of g of 0, but I haven't been given anything to have a plus c or a c plus in the equation. They've given me my equation is starting at 0. So this means the meaning of that is the area accumulated starting where?
So anything on the other side of the triangle?
Not starting at 3,
Starting at 0.
starting at 0. Okay, the area accumulated starting at 0. Okay, before we go to the questions, let's make sure we understand everything else. If that's what g is defined as the integral, but what it means is the area accumulated starting at 0. G prime of x, the derivative. Okay, this is what you should have gotten good at last night. If I move down a level, what is g prime defined as? F of?
No.
Okay, I'm taking the derivative of an integral. This was last night's homework. F of x times the chain rule of 1 minus f of 0 times the chain rule of 0. So all of that's going to clean up. And so g prime works out to be equal to f of x.
That's nice.
They usually work out nice like that. What would g double prime work out to be?
The derivative f prime.
F prime of x. Okay. It is always really important on an FRQ to identify these 3 things. If you are given g, then work down the ladder to figure out what all the other things are, because we're looking ahead and we're going to need to do a g prime, and a g double prime. So it's helpful to work ahead and just have those things worked out. Okay, now we're actually going to use some numbers. So g of -1. If I look back at my box, g of -1 means the area accumulated from 0, the starting point can't change, but ending where? From 0 to -1. What direction is that? That's backwards. That is the area accumulated from 0 backwards to -1. So what shape is that on my drawing?
Triangle.
It's a triangle, but it's a backwards triangle. And so the answer should be negative because I'm working backwards. And what is the shape or the size of the area of the triangle that was going backwards like that?
-1/3.
-3/2. Okay, 1/2 base times height for a triangle. Okay, the next thing it wants me to find is what's G prime. Yeah,
I'm confused.
okay.
From 0 to -1, that's not a trapezoid?
Because
Oh, so it's not counting the area of the entire.
no, because you're going from 0.
Relative to the axis. The axis is the, where would you see a trapezoid?
If you bring the thing down.
No, you have to stop at the axis. You can't go beyond the axis. Anything below the axis is going to be more negative stuff. You stop, it's always relative to the axis. Axis is your cutoff point. All right, G prime of -1. Okay, you're not actually going to answer G prime of -1. What you're going to answer is in the box what you figured out that G prime is equal to. What is G prime equal to? F of -1. F is the graph, the plane graph, not the area, just the graph itself. And what is F of -1 on the graph? Correct. Yes.
So if you're going backwards and it goes below the graph, we can make it positive.
Yes, sir. And then G double prime of -1, our little box tells us that G double prime of -1 is going to be answered equivalent to what? F prime of -1. And how am I going to get, what does F prime of -1 mean if the graph is F? The slope. And so what's the slope slicing through -1? Right, up 3/1. So the answer is like that. Okay, we're just going to practice. Okay, let's try. Okay. Same graph, same equation. Let's just quick jot these things down here again so we've got them. That G prime was the same as f of x. And then G double prime is the same as f single prime. Okay. I'm not even going to look at the graph right now because I want you to... All right. Question is, for what values on -2 to 2 is G increasing? The best way to answer this question is to know, is why I was forcing you to understand your justifications from first semester. How do you answer when anything is increasing? What would be like the blanket statement that covers it? G is increasing. How would you finish that?
From blank to blank.
Okay, how about that? Let's answer the when first. G is increasing when what happens? When G prime is positive. That is the blanket statement. G increases when G prime is positive. Now, looking back at, I'll put a box around it again. What is equivalent to G prime? F of x. So what I'm going to do is, you can use your notability. It won't let me. Okay, I was going to insert it. Slide your is positive over. G prime, I'm going to change that to f of x because they are equal. Those two things are synonymous. So G increases when f of x is positive. Where's f of x? What is f of x? F of x is the graph. When is f of x positive? Okay, positive just means above the x-axis. That's what positive means. Okay, so when is the graph itself positive? The graph itself is positive on -1. No. No, thanks. -1 to 1. So I just covered my explanation and I answered it all in the same thing. Know your reason. Sometimes it's better to know your reason before you look to answer the question from the graph. Let's try another question. Same graph, same thing. I'm going to recopy my stuff again one more time. That G prime is equal to F and G double prime is equal to F of prime. Okay, the question is, for what value is G concave up? So don't distract yourself by looking at the equation. Don't distract yourself by looking at the graph. Just answer the question. G is concave up when what is true? When G double prime is positive. Okay, now in this particular situation, what is G double prime equivalent to? F single prime. So change that to F single prime. Now answer the question. G will be concave up when F prime is positive. What does F prime stand for? The slope. So looking at the graph now, where do I see the slope being positive?
-2 to 0.
From -2, this whole section right here has positive slope. From -2 to 0. Okay, a lot of times students get distracted by the actual equation or the picture instead of just answering, trusting the math that they know, trusting what I know to be true, write out the explanation, and then go back and do some replacing and then figure it out. We're going to try it again. All right, here we go. Different picture now. Okay, best thing to do, start over here. G is defined as something related to the picture. Is G the same thing as the picture? No, it's described as something related to the picture. All right, the description is start counting out area starting where? At 2. Okay, area starts at 2. So that is important for you to, area starts at X is 2. That's important. Also important for future answering of questions is for us to identify what G prime and what G double prime are both going to be. So G prime would be what we did yesterday. Take the derivative of that integral. So that takes f of x times 1 minus f of 2 times 0, which essentially wipes all that stuff away and we're just left with f of x. And then just like before, so then the second derivative is prime. Okay, those things, having that, like answering an FRQ or something, that is key to answering your question. Okay, then I'm still not even gonna look at the graph. I'm gonna go to what the question was. Find all intervals for which G of X is less than 0 on this whole graph. All right, G of X will be less than 0 when? All right, well, when is anything less than 0? When it is positive? Okay. When G of X is negative. Okay, that's just a basic truth. G of X, something is less than 0 when that same something is negative. All right, what can that same something be replaced with? What is that something equal to? The integral starting at 2. So I can say not just when G of X is negative, but when the area under f of x starting at 2. Okay, so you've got notability you can move at and make it better. Okay, so I'm going to answer this question. I'm looking for area starting at 2 that turns out to be negative. All right, so let's look at it. Now let's look at our graph. Here's where I'm starting at 2. If I go 2 forward, what kind of area do I get? All right, so it's not 2 forward. It's not forward to 2. Okay, if I go 2 backward, what kind of area do I get? Okay, if I go backwards here, what kind of area is that? No, it's not positive area. I'm going backwards. That is negative area. Okay, when we run negative, okay, when does it switch to being positive area? Down here. Now, is there enough positive green area to wipe out the negative area? Shape-wise? What is there more of? More negative area or more positive area? Okay, it's more negative area. So all of that has a net value of being negative. It's negative from 2 backwards to negative 2. And it continues to be negative when you accumulate everything all the way to the end, all the way to negative 4. So that whole section is negative. All right, so what intervals will it be negative? We just identified everything from negative 4 up to positive 2. That whole thing's going to have negative values. Okay?
It's written that way. You don't need like.
No, when you write an interval, you still have to put the lower number on the left. But we are by the definition of the integral means as we read the area, we start at 2 and go backwards. Okay, now let's try going forwards. What if I go from 2 forward to 6? What kind of area is that?
Positive.
It's positive. Okay, what if I go to 8?
It's negative.
Well, that little bit is negative, but is it enough if you're accumulating?
No.
So you've got from 2 to 6, which is a positive, and then from 6 to 8 is a little bit negative, but what overall is that net result? Is there more positive or negative? It's more positive. When does it finally get a net result back to where they cancel each other out? Okay, now I'm back to 0 area again. What if I keep going? Okay, if I keep going, then this part will be negative. And so the other answer to this is also from 10 to 12. That will also have a net result of accumulated negative area. Yeah, Edson.
Why is it negative 4 to 2 on the first one when there's like the positive sections but not on 2 to 12?
Okay. If I ask you to go, okay, remember everything starts at 2, right? If I say go 2 backwards to 1, okay, you can let me look at the picture on your thing. Is that going to be positive or negative?
Negative.
Okay. If I ask you to go 2 backwards to 0, okay? If I ask you to go 2 backwards to negative 1,
Still negative.
okay? If I ask you to go, oh, I lost my ability to, okay, what if I ask you to go to negative 2?
Negative.
Okay, what if I ask you to go to negative 3?
Parts are positive.
Okay, parts are positive, but is enough positive, what's the net result?
Still negative.
Still negative. And then if I ask you to go all the way back to negative 4,
Still negative.
still negative. So every value between negative 4 and 2 is going to result in a negative value. We still write our answer in numerical order where the smaller one goes first.
Okay.
Okay?
But like from 2 to 12, if you combined all of that, wouldn't all of that be,
If I go from 2 all the way to 12,
wouldn't that total be negative?
uh-huh.
So why did we do that?
Because it's the values that you're putting up at the top. The bottom, the 2 on the bottom is fixed. Our interval is representing what the possible top values would be.
Oh, so
X represents the top value. If you want me to call it B, I can call it B if you want.
Oh, okay.
We're saying what values would go on the top
Go on the top.
of this. Okay, X is defined. Our axis is not X. Our axis is t.
I see.
Okay, x is representing, so maybe you want to think of it as b instead. What values would be on the top that would produce a negative value?
thank
Okay,
you.
yep. All right, try again. Same picture. Find the absolute maximum for g, okay? G has an absolute max when? Go back to your definitions from first semester. When does anything have an absolute max? Okay, when G prime changes from positive to negative. Okay, that is true statement. So G prime, according to this problem, is equal to what? And maybe you have to go back to your other slide because we didn't rewrite it. Okay, when f of x. Okay, so G will have an absolute max when f of x changes from positive to negative. Do you see that happening anywhere on your picture?
Yes.
Where? Anywhere else besides 6? Okay, this happens at 6. What about the endpoints? Okay, what about the endpoints? Okay, what was happening at 12 from the previous slide? If we went all the way out to 12, what was happening? I listed them all out. When we go all the way from here to here, more negative or more positive? It's more negative when we get all the way to the end. There's more negative answers, so that can't be an absolute max. And then what about when we went all the way out to that end point? Was it more negative or more positive? More negative, so that can't be an absolute max either. So we only have one absolute max. All right, what about absolute min? G has an absolute min when G prime changes from negative to positive or is an endpoint. All right, and we know that that is the same as f of x. Is there any place where the graph is changing from negative to positive? Where? Okay, at -2, which is a possibility, but we also know that -4 is a negative value. We also know where else is a negative value? 12. That's the other endpoint. You have to think about the endpoints. Okay, so we decided that -4 and 12 were endpoints, but they were not, neither of them were maxes. But -4 and 12 are both mins, so those are both possibilities as well. How are you going to actually determine which one is the absolute min? You'd have to actually figure out the geometry and figure out who has the smallest number. Okay, who has the smallest negative value, and you'd have to actually calculate the geometry. All right. So let's look at what's going on at 10. Okay, what would it require to have, right, a relative min or max or neither at 10? That there must be some kind of change. So there must be a change in G prime to have a max, min, or neither. But if there's going to be a change in G prime, we change G prime to what G prime stood for. And G prime was the same as f of x. So there has to be a change in f of x. All right, so now we look at what's going on at 10. And there is no change in the nature of f of x at 10. It's negative and then staying negative. So since the values let's see, of f of x for x less than 10 are negative. And the values for f of x for x greater than 10 are also negative. There is no demonstrated change. Okay, so then it can't be either a max or a min there. So that might be one way to describe it. Of course, there's other ways you guys can describe it. You guys are getting really, really good at writing your justifications, but there's a sample. Does G have a point of inflection at 4? Okay, well, what has to happen there? So there needs to be a change in G double prime to have a point of inflection at 4. And what was G double prime? Well, G double prime is the same thing as F single prime. So there needs to be a change in F single prime. F single prime would be a change in the slope of the graph that we're looking at. So let's find where 4 is. And I do see a change in the slope of the graph. So since the values of f prime of x when x is less than 4 are positive, and the values of f prime of x, excuse me, at x is greater than 4 are negative, so there's negative slope now. The values of G double prime are also changing in the same way, which means there is a point of inflection. Oops, an inflection point at x equals 4. All right, there we go. All right, new graph. All right, so we have a new graph, curved and shaped. What is the meaning of the defined function s of t? All right, so s of t is defined this way. What is the meaning of that? It's the accumulation of area under f of x starting at x is 0. All right, so we know that because the lower bound was here, and that's what we're looking at on the x-axis. So determine the velocity and the acceleration functions. So that would be kind of the same thing that we have been doing now. So the velocity function has to be the derivative with respect to time of s of t, which would be the derivative of this integral. And the derivative of that is going to be f of t times 1 minus f of 0 times 0, or clean all that up, and so it's just f of t. And that means the y value on the f of x function. And then the acceleration would be the second derivative of that, which would be the derivative of the derivative, so f prime of t, which means the slope of the F graph that we're having. Okay, so as long as we're defining everything and we're getting straight on what everything means. Okay, so then you can use that to answer the question. What is the initial position? So that would be S of 0. So when time is 0, what is the position? Then the next question is, what is the position at 3? So that would be S of 3. And then when will the particle return to the origin? All right, well, let's answer the first two questions. S of 0 would be the integral, the accumulation of area starting at 0, ending at 0 of f of x dx. So the initial position is 0 because you can't accumulate any area if you start and end at the same point. S of 3 would be starting at 0 and ending at 3 of f of x dx. So starting at 0, ending at 3, and the accumulation of area there, that's going to be a negative triangle. So that would be negative 1/2 base times height. The base is 3, and then the height of that triangle is 6. So that would be -9. That's the position of the particle. So when will the particle return to the origin? All right, so the particle has started at 0. That's the initial position. It's moved to -9. So now we've moved backwards. So when will it come back to the origin again? So it has to regain all of the negative position that it's lost. And so we regain it by covering an equal amount of area in a positive sense. And so the particle will return to the origin at time equals 6. Because the negative area cancels out the positive area, which means its displacement is 0. It's right back where it started again. Its total distance traveled would be 18. That would be the absolute value of -9. That's this one. And the positive 9, so the total distance would be 18. But the net distance traveled is going to be 0 because of the cancellation. When is the particle moving toward the origin, and when is the particle moving away from the origin? So moving toward the origin means that it has to have both, well, its velocity and its position have to be opposite from each other. Okay, its velocity and its position have to be opposite. And then away from the origin means its velocity and the position have to have the same sign. So we have to compare what's going on the velocity and what's going on the position. So we have some critical points here. Our critical points are 0 to 3 and 3 to 6, and then what happens from 6 to a little bit more than 9. So let's take a look at that. So I would probably set up a chart to think about that. So 0 to 3, I'd also look at 3 to 6, and I'd look at 6 up to a little bit more than 9, so 9 plus. And then we want to know what's the position and what's the velocity. So remember, the position is S of t, and the meaning of that is area, and the velocity is v of t. Okay, and remember that v of t is the derivative, so that would be f of t times 1 minus f of 0 times 0. In other words, f of t times 1. All right, so let's analyze all of that. So the position from 0 to 3 is the accumulation of area. So we've already talked about that, the accumulation of that area. And so then that would be negative. So I'll put a negative here. Okay. And then now we're going to be having accumulation of area here. Okay, now this is where it's tricky, okay, because some people want to put a plus here, but that's not true. It stays negative because as you move from 3 all the way to 6, so say you've moved a little bit farther, the accumulation is all of it combined. It's not just 3 to 6, it's all of the values all the way across there. And so it's going to be negative the whole time. until it gets to 6, and that's when it returns to 0. We already said that in a previous problem, or on the previous slide, that it was going to return to 0. So right here is where it gets back to 0 again. After that point, now we're accumulating positive area because we've gone far enough to where we've canceled out the negative area before. So now I have my positive area. Okay, velocity. Remember what velocity is defined as. Velocity is defined as the y value. This is the accumulation, but velocity is the y value. So from 0 to 3, all of the y values are negative. From 3 to 6, all of the y values are positive. And from 6 to 9 plus, all of the y values are positive again. So if we're comparing movement, when the particle is moving toward the origin, the only time it's moving toward the origin would be here because those are the same sign. And so this is a towards. And then we have 2 times where the particle is moving away because it's sharing the same side. So that would be moving away from the origin in a negative direction. And then we're talking about away from the origin in a positive direction. So the particle started at the origin. So if we think about where it started, if we kind of tell the story, it's starting at the origin. It moves away from the origin for a while. It turns around and moves towards the origin. It comes back to the origin right here in the middle. And then it moves away from the origin again for the rest of the time. So on which side of the origin does the particle lie by the time we get to time 9? And it's going to be on the positive side because of the way we know how the story went. You have to imagine, here's the origin, and I've got a little particle starting here, and it starts out going away from the origin, and then it turns around, and then it comes back, and then it returns to the origin. Now I'm at time 6. And then I keep going past the origin for the rest of the way. So I end up on the positive side. Last slide. So what's the velocity of the particle at time 3? So again, remember that the velocity is the same as f of t, which is the same as the y value. So v of 3 is going to be the same as f of 3, and f of 3, according to the picture, is 0. So the velocity is 0 at that point. And I don't have any units to use. I only have time, but I don't have any distance units. What is the acceleration of the particle? So the acceleration at time 3 is going to be the f prime at value 3, which is the slope. And the slope of that picture right there is your count. Okay, how much am I going up? And how much am I going over? The slope right there is 2. It's up 6 over 3, so that's over 2. So what does that mean about the particle's movement at that time? So we compare the velocity and the acceleration. So at time 3, the velocity is 0. It's still. The particle is, we say, at rest because it has 0 velocity. But it's getting ready to move forward because it has positive acceleration. Okay, so it's at rest at the moment, but it's preparing, it's just about to move forward with positive acceleration. All right, so I hope some of those strategies about sort of decoding these graphs is helpful to you. If you want a different explanation, you can always watch a previous video. I would maybe recommend the 2021 video. That was the year we were doing hybrid learning, and so that was a pre-recorded video. So if you felt like you didn't get it the first time, that might be a helpful thing for you to watch too. All right, thanks. Hope you guys have a great weekend.